electrons. Okay. So, yeah, neon is 2,8. Where are we? Fluorine, 2,7. Chlorine, 2,8,7. Bromine, 2,8,18,7. Argon, 2,8,8. Carbon, 2,4. Boron, 2,3. And hydrogen, just 1. Good. All right, and valence electrons. Here we go. 2. I'm gonna go quick, so if I make a mistake, let me know. 2, 5, 2, 1, 8, 7, 7, 7, 8, 4, 3, 1. Questions on that sheet? Okay, you can put that away. Take out your notes. I got some things I want to show you. I think we're going to summarize all the history talk again, understand what models we should have kind of sketched in our notes, and then I have a couple images of the current wave mechanical model. And then I think I will show you Thomson's experiment, Rutherford's experiment, and then we will take some notes on Dalton's atomic theory. And if we have any time left, I'm going to talk more about this, how the protons always equal the electrons, except sometimes the electrons can change, whereas the protons can't because they're stuck in the nucleus, and that strong force doesn't allow them to leave, and it doesn't allow to gain any. So we'll talk more about that maybe. If we do, that'll be your homework, kind of questions about what happens if those numbers change for the electrons. We'll see. All right. I'm not too optimistic because I talk a lot and I want to show you some things. So, questions for me? Okay. Hello. So, who was the first scientist to start talking about atoms? Democritus. How long ago? 460 BC, so at least 2,460 years, right? Long time ago. Who was next? John Dalton. Who was next? J.J. Thomson. Next? Ernest Rutherford. Next? Niels Bohr. And then the most current model. What's the most current model called? Wave mechanical model, or quantum mechanical model, or the electron cloud, and Heisenberg and Schrodinger had a lot to do with that. There's two other people back around Thomson, Rutherford. You don't need to write it down, but I just feel like I got to give these guys credit. R.A. Millikan. Millikan did an oil drop experiment where he figured out the charge and the mass of an electron, which is crazy. So if we have time, maybe I'll show you that too. And then James Chadwick. James Chadwick helped discover neutrons and protons. So they're also part of it, but for some reason they're not really talked about a lot in regents or on tests or anything like that. So really, Dalton, Thomson, Rutherford, those and Bohr. Dalton, Thomson, Rutherford, and Bohr are the main ones we talk about. The three models that we should have at least sketched in our notes, and I'm going to put it up here on the board. Thompson's model, what was that? Plum pudding, right? So if you already have this, you don't have to draw it again. But here's your plum pudding model. This was Thomson. That's a bad P. The plum pudding model. This is kind of hard to show it on the board, right? But this area here is like pudding consistency, and the whole thing is positively charged. That's what the big plus looks like, or what it's for. So this is the positive pudding, right? That was what he thought. And then stuck in the pudding, he used plums as an analogy, were negative electrons. So the electrons were kind of stuck in there, and the electrons were not moving. We know that's wrong, so that negative sign would be the negative plum, and that's the electrons. That's an electron. That's what Thomson discovered was an electron. So I actually do have a video of some teacher, I don't know, he kind of did the same thing I do, recorded himself doing a demo. So I'll show you that experiment, how they discovered the electron. So that's the plum pudding model. That was Thomson. What was the next model? What was the next one? after they realized that that isn't right. The what one? Yeah, but that wasn't the model. That was an experiment. But there was another model after this one. Yeah, the Bohr model. Bohr model was the next one. So the Bohr model, that's the one that people typically think of. You have a central nucleus with these, what did he call them? What did he call those? He didn't call them shells or levels. He was wrong, but what did he say the electron did? Orbit, right? He said these are the orbits of the electrons. So he admitted, not admitted, but he knew that there were, I'm just putting E negative here, there are electrons on these energy levels, these shells. So I guess, he did say that. He did say there were levels, so that was very, very good for back then. But they do not orbit. I'm going to make it very clear, they do not orbit, but there are these levels. And you guys remember how many electrons per level? And remember how many on the first level? Just 2 electrons. Let's put a 2 there. 2e minus. What about the second? 8. Next? 18. 32. And then the 5th, 6th, 7th, there's 7 of them, right? 7 periods, 7 levels. They have 32 as well. And in lab class this morning, we talked a little bit more specifically about where exactly those electrons are located. And we'll talk a little bit today in class about it, but in lab we'll really get into detail on that. So we got the plum pudding. Parts of it were right. Positive, negative, we know there's positive and negative, but that wasn't right. Parts of this, correct. There's a nucleus there. Rutherford helped find, right? Rutherford said it was positive nucleus. So we know there's levels, but they do not orbit, and there's more to it. These electrons actually are confined to these little spaces moving around. So that's, getting closer. And now the most current is the wave mechanical model, or the electron cloud, or quantum mechanical. I hate giving you 3 names for the same thing, but you need to kind of be aware of them. Does anyone know what the word quantum means? You ever hear of the show Quantum Leap? It's old. Nobody? Oh, man. It was like my favorite show in the world when I was a kid. Of course, you wouldn't know except when I was a kid. This guy, Sam Beckett was his name. The actor is, I can't believe I can't remember his name right now. He's on like CSI New York right now or something like that. What's his name? Anyways, he was this nuclear physicist or some super smart physicist, and he discovered a way to time travel. And quantum leaping, what that means is when electrons jump to higher energy levels. So the show was based on a whole lot of, science that they're making up, I guess, where he literally would quantum leap and his body would change into someone else's body. So he would time travel, but turn into somebody else. So in the show, every show in the beginning, he would just beam into someone else's body and he would have no idea what's going on. So one of my favorite ones is when he leaps into a boxer. So he's in the middle of a boxing match and he's like, what? And the dude just knocks him out because he doesn't have any idea. Sometimes he leaped into women's bodies. That was interesting. So when he looked in the mirror, he looked like someone else. Anyways, I get excited talking about it because it was an awesome show. And it always makes you think of it. Quantum leap is what it was called. And quantum leap is a thing. You need to know what that means. So quantum, back to my question, what does quantum mean? It means energy. A quanta is a bundle of energy. Quantum is basically a single unit of energy. So the quantum, the energy mechanical model, wave mechanical model, basically the easiest way to draw it is you have a tiny, tiny, tiny positive nucleus and then just a bunch of dots which represent electrons. So the electrons have a certain density. So it's kind of hard to show you with one example, but the density of this cloud of electrons changes depending on the atom and depends on where we're looking in the atom. But in general, you have your nucleus here. You can't really tell, sorry. You have your positive nucleus here. And then all the electrons around it buzzing randomly on their levels in these little areas called orbitals. So Bohr, so be careful here. Bohr said the electrons orbit. They do not orbit. However, these electrons are confined to these little spaces. And those little spaces the electrons are stuck in. These little spaces are called orbitals. And I want to make sure we write that down today. I think before we drew these, last thing we had was Heisenberg and Schrodinger, right? That was the last thing we wrote. So I'm just going to continue a little bit with that and talk about this. But yeah, these electrons are found in these spaces called orbitals. We can write that in the picture here somewhere. Orbitals. It does not mean they orbit. I know that's confusing. But they do not orbit. It's just the name of the area they're confined to. So that's the most current model. And I got a couple pictures I'll show you of that, just so you have a better understanding, because that doesn't really do a good job. Questions for me before I erase? So, was it easy to come up with a model for humans? Was it easy for us? What's the proof it was not easy at all?
Took us like a bunch of years.
Took us a bunch of years. Yep. Going on 3,000 years. Okay. 2,500 years it took to come up with something we think is right. Right? I mean, I bet back then they were like, that's right. That's got to be right. Nope. That's got to be right. So now we say, oh, that's got to be right. This was taught not too long ago. Okay, my grandparents, they were learning about atoms. I bet that's what they said, and this is how it is. They said the electrons orbited. Okay, not true anymore. And that wasn't that long ago. So we're getting pretty good with our technology, though. So we're probably getting pretty close to exactly the way it is. But anyways, took a long time. Wasn't so easy. Lots of different people contributing. All right. So I want to add a little bit more about this, and then I'll show you some things. Then we will move on. All right. So we're kind of just continuing on the current model. I know the pictures might have screwed up your notes, but I guess we can title it here, just so you don't screw up your notes. Wave mechanical model. I want to make sure I word this correctly, because sometimes I do not. Give me a second here. Okay, so electrons exist in a region of space called orbitals. And the probability of finding an electron, this is kind of like the definition of an orbital, sort of, or definition of this model. The probability of finding an electron, which is a really, really tiny subatomic particle, right, with a negative charge. Probability of finding an electron is highest. Probability of finding an electron is where? Where's the probability? If you were to have the ability and technology to look at an atom and you want to find an electron, where should you look?
Orbitals.
In an orbital. Probability of finding an electron is highest in an orbital. It's kind of like yeah, I get it. That makes sense. But that's a phrase that you need to understand. Probability. The probability of finding an electron is highest in an orbital. In other words, the greatest chance of finding an electron is inside an orbital. All right. The orbital is confusing. It's hard for me to really get into all the details right now. I'm not ready to do that with you guys, but we will come back and talk about this more because it's confusing to you. The best way to explain it right now before I move on is imagine students are electrons and classrooms are orbitals. So in school, you're most likely going to be found in a classroom. In an atom, you're most likely going to find electrons in these things called orbitals, which are like little rooms inside the atom. That's the best way I can sort of get you to follow me right now before we go in depth. All right. So hopefully that makes some sense. We're done kind of with the history there, and we're going to move on. I'm going to show you some images and some videos of Thompson, Rutherford, and then we'll just finish with some notes if we have time. All right, so someone get the lights, please. So I'll show you an image of the most current model first. Is anyone else warm? It's like a bazillion degrees in here. It's like 72. That's pretty warm. Oh, and that front window is broken. Don't ever try and open it. I gotta put a sign on that. You get open, it might not close. So first couple images I want to show you is of the current wave mechanical model. And first period might have a little better, first period lab students might have a better handle on this, sort of, because I explained it a little bit. So here's all that math that I was talking about in period 1. Basically, you guys see these different shapes. These shapes are due to wave functions, and that's how electrons move in the atom. The N stands for the energy level, 1, 2, 3, 4, 5, 6, 7. So energy level 1, so that's those, we call them rings or shells, right, or levels. But the shape kind of changes depending on which level it's on. And that's still confusing for me. I admit that. I'll admit it if I'm confused about something. There's a lot of math. They're called wave functions. And these mathematical equations and these weird shapes are responsible for the wave mechanical model, the most current model. That's not what we drew, right? We drew the dots. So what you might make more sense is this, okay? So that's the uncertainty principle, Heisenberg. What is that? That uncertainty principle is basically saying the last sentence we wrote. The probability of finding an electron increases inside an orbital. The other way to say that is the greatest probability of finding an electron is in an orbital. If you notice, where is the electron density greatest in that picture? The electrons are the green dots. Where's the electron density the greatest? On the outside of that cloud or on the inside of that cloud? Inside. Guess what's in the middle of that electron cloud? The nucleus. What's the charge of the nucleus? Positive. What's the charge of an electron? Negative. Very interesting. Why is it more dense towards the middle? Marcy.
They're more strongly attracted to the nucleus.
Right. They're more strongly attracted to the nucleus. Well, how come electrons don't just get sucked into the nucleus and atoms just blow up all the time? Because they're confined to those little spaces. What are those spaces called? Orbitals. If you take away those spaces, they could get sucked in. Okay? So those orbitals actually keep the electrons in a certain little area. But in general, the electrons are attracted to the nucleus because opposites attract, positive, negative. So that's more like the cloud, electron cloud, the most current model. Okay? All right. So let's see. What am I going to show you now? Where was it? J.J. Thompson. Okay, so J.J. What did J.J. discover? The electron. Here's how they did it a long time ago. This is more current though. Oh, I thought I had a different video. Alright, this one works too. It's kind of grainy, sorry. This guy's awesome.
Brooks tube, which has a metal cathode, a metal anode, a screen that has been coated with a phosphorescent material that gives off light when struck by electrons, and a bar magnet. As we turn on the screen, we notice that the electrons are emitted from the cathode, and as they strike the fluorescent screen, we're able to see the cathode ray.
Okay, so essentially, if you've ever heard of cathode or anode, it's like the positive negative terminal of a battery. So the electrons come from the cathode in this experiment because he's hooked up to a power source. That beam of that you see is a beam of electrons. There's a special screen here.
Pardon the interruption. Can we please have the high school band members report to the auditorium for pictures? Thank you.
That's everybody? Alright, you're gonna miss the exciting conclusion.
It's almost.
Yeah, bring your stuff.
I just recorded.
Everybody have a good Thanksgiving.
You too.
Apple or pumpkin?
Neither.
Neither.
I'll say pumpkin.
I go pumpkin on that one.
Yeah. Are you going with the game tonight?
I can't.
Alright. We got tape. We'll tape it. You watch the tape.
What do we got? We got Healy?
Yeah. Hopefully we can speak out a little.
Yeah, well, you know, we're
Yeah.
taking too late.
Yeah, I know.
Anything can happen.
Yeah.
Every year.
Alright, so back to that. I'll explain it to you guys. I'll probably show this again Monday. So we might as well finish it. Alright, so anyways, that screen is coded so that you can see the beam of electrons. Essentially, it's like a beam of electricity. That's what electricity is made of, electrons, basically. But anyways, there's a beam of electrons, and he's going to bring a magnet near it.
This stream of electrons illuminated. We can use a magnet to show the deflection of that stream. Here we can see the electrons being deflected by the magnet. The cathode ray moves upward. If we reversed the magnet, we would predict that the beam would be deflected in the opposite direction. And we observe that the beam is deflected downward.
So if you have one pole of the magnet, it deflects away. If you reverse it, it deflects towards it. So a long time ago, Thomson did the same basic experiment, not even on purpose, I don't think. He was just doing experiments with gases and electricity and realized that the beam moved based on a magnet being brought near it. And that told him that must be made of particles with charges. And then ultimately they discovered it was an electron, it had a negative charge. So that's called the cathode ray tube experiment. And that's what they did a long time ago. So I guess I'll stop because what else, you know, I'm missing like everybody. So I guess no homework. We didn't get to...
Can I have that worksheet that was due today?